Cool. All right, so today I'll be presenting my work, Revisiting the Proof System. This is joint work with Dan Bonet and Trion Setti from Stanford and Microsoft Research. So today we'll be discussing incrementally verifiable computation. So this was introduced by Valiant in 2008. And the goal is to efficiently improve the outcome of some continuous iterative computation. So what does that look like? Basically, you have some base element, Z0, and you repeatedly apply some type of step function f, and you prove that Zi is the claimed evaluation after I iterations of f. So what are some modern day examples of these sort of iterative functions? One case is verifiable delay functions. So for a very slow to compute f, does the ith iteration of f on some base case Z0 equal to Zi? And state machines, so ZK EVMs, for some straight transition function f, does state I actually equal to the ith state after you apply the state transition function I times? So our work, revisiting a node proof system on a cycle of curves, introduces a soundness vulnerability in the Nova proof system, in which we are able to successfully fake 2 to 75 iterations of the min root VDF in only 1.46 seconds. If the Nova implementation had been secure, this would have taken thousands of years. So the fact that we were able to produce a proof that verified means that the implementation actually had a soundness vulnerability. Plus, we introduce a compiler from folding schemes to IVC over a cycle of curves. So what should you take away from this talk? What are folding schemes, roughly? How is IVC constructed from folding schemes? What changes when we introduce a cycle? And what was the soundness vulnerability in Nova? But first off, in order to introduce folding, I have to do some review on constraint systems. In particular, the constraint system called relaxed RNCS that was introduced by Nova. So RNCS is a constraint system which is comprised of 3 matrices, A, B, and C, and an instance witness pair XW over the field satisfies this constraint system if the matrix product of AZ, Hadamard product BZ equals CZ for Z, which is the concatenation of W, X, and 1. So I believe people are familiar with this. But Nova introduced the notion of relaxed RNCS, which just improved the efficiency of folding. In fact, BCLS 21, which I believe is the accumulation schemes, also had a folding scheme for RNCS, but not for relaxed RNCS. So a relaxed instance witness pair, instead of just an X and W over the field, is now this U and W, where U is comprised of a commitment to the witness vector, a commitment to this E vector, which we'll call the error vector, and X and S, where S is some type of scalar. W is the witness for relaxed RNCS, will just be an error vector E and a witness vector W. So what does it mean for this pair to satisfy RNCS? If we set Z to be the concatenation of W, X, and S instead of W, X, and 1, AZ, Hadamard BZ, is equal to the scaling of CZ plus some error vector E. Also, the commitments in the instance must actually be commitments to that error vector and to that witness vector. And so, additionally, when we look at a relaxed instance, we can also say that this relaxed instance is strict or not. If the error vector is 0 and S is 1, we basically just recover the original R1CS equation. It's just AZ Hadamard BC equals CZ. So the intuition of folding schemes is given some instance witness pairs UW1, UW2, the prover has both of these instance and witness pairs, and it wants to convince the verifier that both U1 and U2 are satisfiable by some witnesses. So we would like an interactive algorithm that somehow reduces the claim that U1 W1 and U2 W2, reduces the claim to the claim that a different pair, UW, satisfies RNCS. So if this UW pair satisfies RNCS, then with high probability, these pairs also satisfy RNCS. In fact, it satisfies a stronger property. We would be given a satisfying pair UW and U1 and U2. We would actually be able to extract these witnesses. So just reiterating, a folding scheme consists of two algorithms: a fold verifier, which takes in two instances, U1 and U2, and outputs a folded instance U. A folding prover takes in additionally two witnesses, W1 and W2, along with the original instances, and produces the folded pair. So why do we even care about cycles of curves? We haven't even discussed cycles of curves at all. Well, if we look closer into that pair of U and W, it consists of group elements for the commitments and field elements for X, right? So it's some field of order P and some group of order P. Now, the folding procedure actually requires taking random linear combinations of elements over the field and elements over the group. So in order to construct IVC, we'll actually need to express the folding verifier as constraints over FP. Now, expressing random linear combinations of field elements as field constraints is pretty easy, but how can we actually express those group operations as field constraints? Now, if we look into the black box a little bit more, what will these commitments be? Like, what is this actual group? Well, this group is actually an elliptic curve group over a different field, FQ, such that FQ is not equal to FP. So what does that mean? Each group element is actually represented by a pair of field elements over a base field FQ, such that they satisfy some elliptic curve equation. Now, expressing these group operations as FP constraints can be reduced to the problem of actually expressing a non-native arithmetic in a field over the base over this other field. So we have to actually express FQ operations as FP constraints. Now, expressing non-native arithmetic is actually quite expensive, and so this motivates sort of the notion of why would we care about what this cycle of curves is? It's because we want to express these group operations as just constraints over the base field directly, because natively these group elements are represented as FQ elements. So what does the picture look like there? Oh, sorry, I first have to introduce what a cycle of curves is. So this is the pasta cycle of curves. So we have one group, GP, whose elements are represented as pairs over FQ. And we have another group, GQ, of order Q, whose elements are represented as pairs over FP. And so why is this called a cycle? Well, the order of GP is P. So that's basically saying the scalar field of GP is FP, and which is the base field of this other group. So the scalar field of one group is the base field of the other group. Okay, and vice versa for both these groups. And so if that didn't work out, I think all you need to know is this slide here. So how can we express folding constraints efficiently? In particular, how can we express the folding verifier efficiently? Well, say we have some constraint system, RNCS1, over some field 1. And respectively, there are these instance witness pairs, UW1, UW2, for this constraint system. Well, in order to express these the constraints to fold these instances, we can express them efficiently over constraints of a different field called F2. And so we can express this folding verifier as efficiently as constraints over some other constraint system, RNCS2, over a different field. And similarly, this constraint system also has their own pairs. And in order to fold those instances, we can also represent, for some reason there was a duplicate slide there. We can also efficiently represent these constraints over the original constraint system. And so there's a sort of diagram chasing here, but the key is, in order to fold instances for RNCS1, we can express that over constraints over RNCS2. And in order to express folding of RNCS2 instances, we can express those as constraints over RNCS1 instances. So we have to do this sort of diagram chasing here. Now, okay, recap so far. We discussed what IVC was. We roughly described what folding was. And we described why you would care about cycles in the sense that they allow us to efficiently describe folding constraints in two different constraint systems. And so now we have enough to introduce our compiler from folding schemes to efficient IVC over a cycle. But we do have to backtrack because that construction won't make sense unless we actually know how IVC is constructed from folding schemes over a single curve at all. So what is the claim that we're trying to verify? So in IVC verification, we're claiming that ZI is the result of applying I iterations of some function f on some base case Z0. So the verification would take a claim, which is like, we've done I iterations. We started off at Z0, and our claimed evaluation after I iterations is ZI. And we have some type of IVC proof pi. And the verification algorithm outputs 0 or 1. So what does it mean to be secure? So given some malicious prover that has some claim and also some IVC proof pi, if the verification algorithm accepts, then we can construct an algorithm called an extractor that produces a pre-image ZI-1 and an IVC proof pi I-1 of I-1 iteration. So what are the properties that these elements have to have? That ZI is equal to f of ZI-1. In fact, that ZI-1 is actually a pre-image. And that IVC proof pi I-1 is actually a successful, or it's an IVC proof for I-1 iterations. And so now with these, the fact that this verification algorithm succeeds, we can actually treat the extractor as another malicious prover, and we can actually induct. So we induct all the way back to the base case, such that we know that ZI was actually produced by I iterations of the function f on Z0. So here's the claim. Okay, so here's the claim. So how do you actually construct IVC? So keep that picture in mind. Ideally, there's some type of constraint system which takes in some ZI and it has a public output, ZI plus 1, and it constrains that ZI plus 1 is actually equal to f of ZI. But that we can't just do that, because if we just check that constraint system, that would only check one iteration. And so this is going to be a little hand wavy here, but we'll make it a little bit more formal later. This constraint system, in addition to actually checking one iteration of the function, will also fold a claim that the last step was done correctly and that all prior steps were done correctly. So we can encode sort of the claim that the last step was done correctly as an instance UI, and we call this the accumulation instance, that all prior instances all prior steps were done correctly. And so what is this constraint system? A little bit more in depth. So R1CS, there's some witness and there's some instance X. The witness will take in the current index I and the base case Z0. The instance contains I plus 1 and Z0. We also take in the previous steps evaluation, ZI, and we apply one step of the function, and the instance also contains the other step, so ZI plus 1. But now we take in, additionally, some strict instance UI that encodes the valid execution of the previous IVC step. And also an instance which accumulates the validity of all prior IVC steps. And then the constraint system constrains the folding of both of these instances into U accumulator I plus 1, and the instance also contains U accumulator I plus 1. And so now, what is the operation of IVC? Like, how do we actually perform the steps in IVC? Oh, sorry, I forgot one point. We can represent the satisfaction of this constraint system here as another instance, U I plus 1, that has no error, and its scalar is 1. So this W will end up being a commitment to this witness, and this X will be all these elements here. So we also, because there's no error and the scalar is 1, this instance is also a strict instance. So UI plus 1 actually ends up being UI, but for the previous step. And so how do we perform IVC steps? We first start off with Z0, and it outputs some type of base case accumulator. We represent this satisfaction of this constraint system as an instance U1. We forward the accumulator here, and we treat that as a witness for another R1CS constraint system. And we perform one step of this constraint system, and we represent this, the satisfaction of this constraint system as U2, and so on and so forth. And so after I iterations, the constraint system should look like this. We take in some I-1 evaluation. We take in an accumulator, which represents the like all the I-1 previous steps. This represents the last step just before. And then you apply one step of the function, and you also fold these instances into this new instance here. And then you can represent the satisfaction of this whole constraint system as an instance UI. So yeah, but okay, so I lied a little bit here. So this is just the previous slide. In fact, we have to keep this instance X constant size. And so in fact, it doesn't actually end up being those items, but actually a hash of all those items there. And so X here ends up just being a hash instead. So going a little deeper into the constraint system. So we've taken our witness, which is our current index, and the base case. We've taken the previous evaluation ZI. We assign variables, intermediate variables in the R1CS constraint system, ZI plus 1 equal to the evaluation of the function. We also take in the two instances. We fold those two instances. And the instance for this constraint system, which is UI plus 1, we just check that X is actually equal to the hash of an increment on the index, Z0, ZI plus 1, which is one evaluation, and the folded instance, U accumulator I plus 1. But additionally, we have to check that UI plus 1, which is the input instance, its X actually is a hash of the current index, the current value Z0, the previous evaluation ZI, and also the old accumulator we took in as a witness. And we also have to check that UI is also strict. So it has no error term. Or I mean, the error term is basically 0 and S is equal to 1. So now how does IVC verification work? So our proof pi will actually end up being the last step. So this is UI, which represents the valid execution of the last step. And U accumulator I, which is, contains the validity of all the prior steps. So the verification algorithm takes in the claim I, Z0, and ZI, the IVC proof pi. It checks if UI is indeed a strict instance, because this needs to represent the validity of the prior step. It checks whether both these pairs satisfy the constraint system R1CS. And then it just checks whether the instance is actually the hash of this claim here, I, Z0, and ZI, and also that this accumulator contained here is actually contained in this instance here. So let's sketch out what the sort of extractor algorithm is and the security argument. So say the verification algorithm actually succeeds. It's actually equal to 1. We know from the verifier's check that UI is equal to 1, both pairs satisfy R1CS, and that instance X is actually the hash of the claim and the accumulator we've checked right up here. And what we have, of course, are the claim elements and the proof pi. So I just pasted that on the top right here. So since we know that that last instance is strict and that we have the satisfying pair UI WI satisfies that constraint system, which I've pasted down here. If we just inspect WI, we'll actually get a couple of elements. In particular, we'll get some index J, some value Z, and some value Z-1, and both these accumulators. Because we know that this pair satisfies R1CS, we end up knowing these properties. One is that the constraint system constrained it such that UI to X's hash is actually equal to J plus 1, whatever that Z value was, and Z prime and U accumulator, where Z prime is actually one iteration of the function, and U accumulator is the folding of the prior steps. This is just enforced by the constraint system. We also know that ui minus 1 is a strict instance because it's enforced by the constraint system, and that its own hash is equal to the prior claim, j, z, zi minus 1, and also this old accumulator, u accumulator i minus 1. So we know nothing yet about the relationship between j, z, z, i minus 1, and this current claim I, z0, zi minus 1. So we have to do some type of collision resistant argument here. So since ui.x is equal to the hash of the index, z0, zi, and u accumulator, this was provided by the actual verification check. And this was enforced because we actually satisfied the constraint system RNCS by collision resistance. Otherwise we would be able to construct a collision resistance adversary. These tuples are actually identical. And so what you'll end up with is if we actually parse the witness wi, it's actually just equal to I minus 1, z0, zi minus 1, and both these accumulators here, such that zi is equal to f of zi minus 1. So we actually know that zi minus 1 is actually a preimage, and that the instances we got as in the witness are actually folded into accumulator I, which is what we was provided to, which is what we were provided in the proof. And we also know these facts here. This comes from the actual constraint system. So the first step of the extractor is just to parse the witness such that these are hold. And then now, what is left? So I put in gray what we've already used. So now the only thing we haven't used from the verifier check is that the accumulator at the last step satisfies RNCS. And what we have is also this accumulator. So what can we do? Since we know that U accumulator I is the result of folding those two accumulators, and we know that pair satisfies RNCS, then both of these pairs actually must satisfy RNCS. And so we can call the folding extractor to extract witnesses for both of those pairs, such that U-1, W-1, U accumulator I-1, and W accumulator I-1 actually satisfy RNCS. So first step, parse the witness. Second step, call the folding extractor. And so now we have a bunch of facts, but how are these facts actually holding up together? So what we have is we have two pairs, UI-1, WI-1, which represent the execution of the ith-1 step, and these accumulators, which represent the prior execution of all the I-1 steps. And what we know is that Zi is actually equal to f of I-1, and that this instance is strict. These both pairs satisfy RNCS, and that its hash value is actually equal to I-1, Z0, Z-1 with this accumulator here. In fact, this is exactly the verification equation, and so we can just recurse from there. So what we've done is we successfully constructed an extractor that outputs a preimage to the ith evaluation and a valid proof for I-1 iterations. So that was Nova. But now, what changes when you introduce a cycle of curves? So instead of one function and one constraint system, you now have two functions and two constraint systems. And so both of these constraint systems, so RNCS1 is over the field 1, and RNCS2 is over field 2. And so I used this notation earlier when we discussed the cycle of curves. And also these two functions now operate over two different fields. So F1 operates over F1 and F2 operates over F2. And so prior in the single curve IVC construction, the claim was that Zi was the ith evaluation of F over on Z. And the proof consisted of a strict instance UI and a strict, a non-strict pair, the accumulator pair, U accumulator and W accumulator. So now for the cycle of curves, the claim is expanded. So now we have two base case values for both fields and two evaluations for both fields. So the claim will end up translating to Zi1 is the ith evaluation of the F1 function on Z0 of 1. And Z2 is Zi of 2 is the ith evaluation, sorry, this should be F2 here, of Z0 of 2. And so now we're basically iterating two functions I times. And then the proof, now all we've changed is we now have one strict instance, but now we have two accumulators. So, and also, okay, so prior, we had one constraint system where X was a hash, but now we have two constraint systems. So in this constraint system, we folded instances that represented this constraint system. But for RNCS1, now we're folding instances from the opposite constraint system. So this, and also, we now, instead of having one hash, we have two hashes. So the instance for U1 will consist of two hashes, X0 and X1. And similarly, symmetrically, we have a secondary constraint system, which folds U1 instances and also has two hashes here. So what will end up happening is now, so the IOC steps are roughly this. So produce an instance which represents the valid execution of one step of RNCS2, feed that into the constraint system for RNCS1, and then now that you've satisfied this, feed that into RNCS2, and so on and so forth. So this executes one step of the F2 function. Here we execute one step of the F1 function. Here F2, F1, F2. And so what's important is that we're feeding these instances to the other constraint system. So now what changes with the constraint systems? So as prior, we take in the index I, Z0, and ZII, and we also take in the instance, which consists of two hashes, X0 and X1. We take in two instances, but from the opposite constraint system. We do one step of the respective function for this constraint system. We fold the two instances from the opposite constraint system. And this is where it differs. So prior, this hash was just equal to this, but now we're introducing this copy constraint. So the output instances, X0 hash, will end up being the input instances, X1 hash. So this is where that little arrow thing came. We're basically doing a copy constraint. So we're moving X1 to X0, and then this X1 to X0. The purpose of this copy constraint will end up so that we end up using the right hash as input for these respective constraint systems, because we have to swap back and forth. Yes, and we also know, this is also in the previous constraint system, we just checked that its X0 is equal to the hash of the input elements, and also that it's a strict instance. And so the reason why we have two hashes instead of one hash now is to juggle the fact that we're going between two constraint systems back and forth. So now how does the verification change with the cycle? So previously, so this was the verification. The claim was this claim. We had some IVC proof of pi. And now we have this claim, which represents the execution of two functions and also an IVC proof of pi. We check that the UI2 instance is strict. We check that all these pairs satisfy their respective constraint systems. But now this is where the major difference is. UI.x, we just check is the hash of the claim plus the accumulator. And that you can see that check is represented on this X1 part here. This is the claim, and this is the instance here. But now we also have to check that X0 contains the claim for this first function plus its own accumulator, plus the opposite accumulator. And so here, this is one hash, and now we have two hashes to check here, in which they're of the similar form, but we've changed this accumulator to 2 and this to 1. Now, I'm not going to go over the full argument for the cycle because it's rather involved. So I'll just do some hand wavy here. So here's the verification in the top right. So we have some RNCS constraint system that has two hashes. If we look at the witness that were provided in the proof, we know that it contains a preimage and two accumulators, which represent one step of the function. And we have a copy constraint here. So X0 will actually end up being the X1 of this instance. So why is that necessary? So or sorry, maybe I'll talk about that in a bit. But first, we need to extract witnesses for these instances here. And so since x1 is equal to the hash of this accumulator here, and we know that this accumulator satisfies RNCS, since both of these input accumulators are folded into that accumulator, we can in fact, we checked one that this satisfied RNCS, and we know that this instance is contained in this hash, which implies that this accumulator is actually the result of folding both of these accumulators, which means since this accumulator is satisfiable, both these accumulators are satisfiable. And so we're actually able to extract 2 witnesses for both of these accumulators. So just reiterating, we started off with some constraint system. We checked that we checked one execution of the function and one folding step. We know that this satisfies RNCS, and since it's contained in the hash, we know that both of these pairs must satisfy RNCS. And so we can actually call an extractor which extracts witnesses for both of these pairs. Now, so that's just step 1. We extracted some preimage and we extracted 2 pairs. Now, if we look at this instance here, which was the input instance to this constraint system, if we inspect its own witness, we get these elements here, a preimage ui-1, and 2 instances for u accumulator i-1, 2 and ui-1, 2. Now, since we checked in the verification check that x0 is actually equal to the hash of u accumulator 2, since these are both the same instances, we know that these hashes are identical. And so I just move the hash check over here. We can repeat the same argument that we did for the other constraint system. And so since this satisfies RNCS, and we know that it's contained in this hash, these 2 pairs are actually both satisfiable because they're folded into this accumulator. And we can similarly extract witnesses for these pairs here. Now, so step 1 is we extracted preimage and 2 pairs. Step 2, we extracted a preimage and 2 pairs. And now we just simply output both preimages and the proof pi, which consists of this strict instance and this accumulator and this accumulator. And so there are some minor points that I didn't argue, which is that these hashes actually end up lining up. But if you believe me, these are actually just the verification conditions. And these are, and this statement here is just that zi-1 and zi-1 are actually just preimages to both of these evaluations. And so we satisfy the verification equations. So although that was a little bit fast, basically the argument reduced to the fact that we extracted preimages and accessible proof for i-1 iterations such that they're actually preimages, and the verification equation succeeds for i-1 iterations. Now, so that seems secure, but what happened in the Nova implementation? So the Nova implementation implemented this sort of cycle of curve strategy, but it didn't actually provide a security proof. And so there was actually a minor difference from what I presented here to what was actually in the code at the time. So on the left here is the secure implementation, and on the right is the non-secure implementation. So this is what Nova was prior. So the difference between both of these proofs is that they included an extra instance ui-1 and ui1 and wi1. Now, this was the prior verification equation, and this is a new verification equation. So the claims are the same, but now they check that this new added instance pair is also strict. They check that this satisfies RNCS, but now here's the vital difference here that caused the vulnerability. Instead of checking that ui2 to x0 is equal to this hash, it checked that ui1 to x1 is equal to this hash. And so, in fact, there are no constraints which check the x0s of either instance. And so that's where it was. That's where things broke. It's as if you had ran 2 independent verifiers. You could just project these checks out, and these instances would not be correlated at all. So if we jump back to our security proof, what goes wrong now? So just to recap the argument that we had prior, we knew that this x0 contained the hash of an accumulator that was satisfiable. So that allowed us to argue that we could extract witnesses for both of these pairs here. But now there's no x0 check on that instance anymore. So in fact, this hash can just be anything. And so we're not guaranteed that these instances are actually satisfiable. And so there's no way we can actually extract witnesses for these instances here. And so what is the actual attack? We can actually generate a malicious proof pi for the claim that these ith evaluations are actually the result of I iterations of both their functions. So we can generate this malicious proof pi for any base case choice. So for any choice of z01 and z02, and any evaluation zi1 and zi2, such that we actually know their preimages. So just to reiterate this, the preimages we can just set to any arbitrary preimage. And so we don't even have to do actually I-1 iterations of whatever function. We can just choose arbitrary values, as long as what we try to claim is that zi1 and zi2 are actually the ith evaluations of whatever base case values that we choose. So the attack is we can cook up some malicious instance ui2 I-1 by just setting the hashes to arbitrary values, such that here we include the z0 of our choice and zi-1 of our choice. And so now we just, this malicious instance doesn't have to it has to be satisfiable. And so we can actually just set the witness and the error vector to whatever we want. And the scalar can just be 1. And so now we just run the honest prover to 2 steps to generate a strict instance ui2, w2, and u accumulator such that they both satisfy RNCS. So it just looks like this. So prior, we had something that looked like this. And so now, since these are not satisfiable, I can just put any arbitrary values here. So in fact, that's just what we do. We just input arbitrary values into the constraint system, and we just run it for 2 executions, such that this pair and this pair will end up being satisfiable, because it's we actually did do the honest prover 2 executions. And so now, so step 1, step 2, and so now step 3 is just repeat the steps, but I flipped all the 2s for 1s and all the 1s for 2s. And then we can just output the proof pi, which consists of all the elements that we maliciously generated. And if you, I didn't argue this, but it turns out that all the verification checks will actually just pass. And so we provide a generic implementation of our attack in this GitHub here for any choice of F1 and F2 functions, any choice of curves. And we demonstrated the exploit against the Nova-based minroot VDF that was provided in the example code. And so here we've produced a successful proof for a claimed evaluation of 2 to the 75 iterations of the minroot VDF in only 1.46 seconds. And so in conclusion, the moral of the story is whenever you implement something, always make sure that it has at least some proof of security, because if you just implement something without proof of security, you may not realize that there could be some very subtle bugs that could just destroy the whole security of the system. And there's now, if you read our work, an efficient compiler from folding schemes to IVC. Cool. And that's the talk. I think I might have gone a little bit fast, but now we have a bunch of time for questions if there are questions.
Yeah, thank you, Wilson. I appreciate it. So Xianfei or anybody else want to ask a couple questions?
Yeah. I guess my question was on the IVC, on the VDF part. So you were saying that you still spend like 1.5 seconds to do the to perform the attack. So if I understand correctly, so for the VDF you actually do the actual computation, the F1 for the VDF, and F2 is just to do the wraps, right? To move it back to the curve to switch between the curves. And so presumably this 1.5 seconds was spent on this moving back and forth between the curves and the actual F1 is skipped. Is that a fair understanding?
So if we look at our attack here, so we actually had to do, oh, sorry, this is not the attack. So this first step, which generates invalid U2 and U accumulator 1 pairs, ends up generating a false proof for the secondary function, for the secondary claim. And then the second execution ends up doing it for the for the first claim. So we actually have to do symmetric work for both curves. So in fact, running the honest prover for only half the iterations would be like whatever 1.46 second is divided by 2. So we actually do have to do work that's symmetric for both evaluations.
Then how do you come up with the 1.5? Like say, if you do need to compute the VDF, or am I misunderstanding? Like my understanding was like in the F1 function, you have a you didn't really satisfy the F1 so that you can skip the whole VDF computation.
Yeah, so we can skip the whole VDF computation for both. It's because the verifier checks, okay, so the verifier checks actually end up being independent of each other. And so this U1 instance is not binded to this U2 instance at all. So we can actually just like execute 2 instances in parallel, like two IVC provers in parallel, because there's nothing that binds both these instances together.
Yeah. So, but my understanding is like you only have the VDF is only computed in F1. In F2, you do not compute the VDF. It's actually the recursion.
So we actually do. Sorry, my bad.
Oh,
Maybe
okay.
yeah. So this first computes. So this constraint system. So we throw away these values here, right? But so we throw away this value here. But this computes one F1 VDF and one F2. Sorry. I get what you mean now. Sorry, my bad. The implementation of the attack, yes. So the min root VDF. Oh, sorry, I get your question now. Sorry, my bad. So the constraints. So R1CS2. So it depends on what field you implement the min root VDF on, but you could have treated F1 and F2 as 2 min root VDFs. But so if you did want to put 2 VDFs, we could fake the execution of 2 VDFs. But in the Nova implementation, one function was just a trivial function that had no constraints, and the other function was the actual min root VDF. So yeah, so we only had to compute one execution of the actual min root VDF. Right.
And then so following that, so the 1.5 seconds is actually spent on recurring a empty circuit. I mean, for many times, basically.
Yes. Okay. So let me see here. So yeah. So each IVC step performed 4,096 iterations, and so I'm not sure how much of this time actually comes from the 4,096 iterations of min root versus the overhead of IVC.
I see.
Yeah. So, but regardless, I guess I could have made this number 1 and still gotten this huge number here. So this is like 2 to the 75. The only reason why I did 2 to the 75 is just because Rust, I didn't want to deal with the size of numbers, and so I just chose the sizes that made it compile.
Yeah. Cool. Yeah. Okay. That's all clear. Thanks. It's really nice work. Would this affect the Ethereum's VDF choice?
Sorry, I didn't get that.
Sorry. Would this? So the VDF, right? Though this will be used by the Ethereum, right? So I'm wondering if this will have any impact on that.
Oh, yeah. So the current Nova implementation is patched, and we also so the current Nova implementation is patched. So as long as the Ethereum folks are using the updated implementation, hopefully things are fine. But if they implemented folding themselves, then they should double check, they should follow this proof and double check that their implementation actually follows a similar style proof. So if they're implementing something that they don't have a proof for, I would be a little bit scared. Yeah, because it's just it's kind of crazy. It's just a very, very subtle change of what you check can just make it completely vulnerable. And so they should be a little bit careful.
All right, cool. Thanks.
I think for now, thank you for joining, Wilson, and sharing about this with the CK Symposium community. Yeah, and thanks everybody who joined.
Thank you for having me.